Today, we are going to get into one of the most beautiful and honestly most powerful ideas in all of physics, Einstein's field equations. We're going to peel back the layers of math and uncover the absolutely incredible story these equations tell about, well, the entire universe.
So let's just jump right in with a question that kind of flips everything you think you know on its head. What if gravity isn't some invisible force yanking you down to the ground? What if, instead, you're just moving along the straightest possible path you can, but through a reality that's been curved and warped? You see, for hundreds of years, we all looked at gravity through Isaac Newton's eyes. It was this mysterious force that just acted across empty space, pulling things together. But then Einstein came along with a completely different take. He said, forget force. Gravity is just what happens when things move through a four-dimensional fabric, what he called space-time, that's being bent and shaped by all the mass and energy within it.
Okay, so to really get our heads around this, here's our plan. We'll start with how gravity was reimagined. Then we'll dig into how matter actually curves space-time. We'll decode the equation itself. I promise it's not that scary. We'll look at Einstein's biggest blunder, see all the wild things the equations predict, and wrap up with why they're still so incredibly important today.
All right, first up, the central idea of general relativity. It sounds really complex, but the main takeaway is simple. Matter tells space-time how to curve.
Let's use the classic analogy here, because it's a great one. Picture the entire universe, all of space and all of time as one giant flexible sheet, kind of like a trampoline. This is our space-time fabric.
Now, if you put something heavy on this fabric, like a bowling ball representing a star, what happens? It creates a dip, a curve. The heavier the object, the deeper the curve. This is the first half of the whole idea. The stuff in the universe tells the fabric of space-time how to bend.
And here is the genius part. That curve you just made now tells other objects how to move. If you wrote a little marble near the bowling ball, it's not being pulled by a force, it's just following the curve in the fabric. That path, dictated by the geometry of the curve, is what we feel and call gravity.
So, this beautiful two-way street, this cosmic conversation between matter and geometry, that's exactly what the Einstein field equations describe. They are, quite simply, the mathematical rules that connect the shape of space-time to all the stuff floating around inside it.
So, what does this conversation look like when you write it down? Let's take a look at the equation. And again, don't think of this as a test you have to solve. Think of it as a sentence we're going to learn how to read.
And there it is. Yeah, I know, it looks a little intense, but the fundamental idea here is just a perfect, simple balance. It's basically a cosmic equal sign.
It really helps to think of this equation in two halves. Over on the left, you've got the geometry side. This part is all about the shape, the curvature, the structure of the universe. And on the right, you've got the matter and energy side. This is all the stuff, planets, stars, light, you name it.
So here's the absolute key takeaway. The equation is an instruction. The right side, all that matter and energy, is literally telling the left side, the geometry of space-time, how to bend and curve. It's a dynamic cosmic dance, and this one equation is the choreographer.
But, science is never a perfectly straight line. The story of this equation has a really fascinating, very human detour in it. A part that Einstein himself would later call his biggest blunder. It's actually a great story about how science works.
So here's how it went down. Back in 1917, Einstein's own equations told him the universe should either be expanding or contracting, but everyone back then knew the universe was static, so he added a little fudge factor, that lambda symbol, to kind of hold the universe still in his math. Then, in 1929, Edwin Hubble comes along and proves the universe is expanding. Einstein, a bit embarrassed, scraps the constant. But then, fast forward to 1998, astronomers discover something shocking. The universe's expansion is speeding up. And to explain that, they needed to put lambda right back into the equation.
The irony is just perfect. Einstein reportedly told another scientist that adding that little term was the biggest blunder of his life. Turns out, his biggest blunder might have been one of his most brilliant predictions.
So what is this thing? Today, we think lambda represents the energy of empty space itself, sometimes called vacuum energy. It acts like a kind of cosmic anti-gravity pushing everything apart. His mistake accidentally pointed to one of the deepest mysteries in the cosmos.
And that accidental prediction was just the beginning. I mean, once physicists really started digging in and solving these equations for different situations, the things they found were, well, they were straight out of science fiction.
The equations predicted black holes, places where gravity is so strong that space-time curves infinitely. They predicted gravitational waves, actual ripples in the fabric of spacetime traveling across the universe. They confirmed the universe was expanding, and they predicted gravitational lensing, the idea that a massive object could bend light like a lens. Now, here's the most amazing part. These weren't just weird ideas that fell out of the math. Every single one of these mind-bending predictions has now been observed in the real universe. We've taken a picture of a black hole. We've detected gravitational waves. The equations actually work.
Which brings us to our final question. Why does a set of equations from over 100 years ago still matter so much? Why is it still the absolute foundation of how we see the universe?
Well, for one thing, a great theory doesn't just destroy the old ones. In everyday situations, like here on Earth with relatively weak gravity and slow speeds, Einstein's equations simplify down and perfectly match Newton's old law of gravity. It contains the old theory within it and explains why it worked so well for so long.
I mean, think about their journey. They were published in 1915 and completely rewrote the rules of gravity. They gave us this stunning new picture of matter and geometry in a cosmic dance. They've since become the go-to tool for modeling everything from black holes to the Big Bang. And even today, they are the absolute core of cosmology.
So, in the end, these equations are so much more than just symbols on a page. They are our deepest, most accurate description of the universe's blueprint and the story of how it came to be.
It really makes you wonder, doesn't it? For over a century, these equations have guided us to one stunning discovery after another. So the real question is, what secrets are they going to help us unlock next?